Hello everybody, this is Mr. Wakefield again, and we're continuing on with our discussion of radicals with adding and subtracting radical terms. Adding and subtracting radical terms is very similar to combining like terms. Okay, let me show you what I mean by that. Looking back at a problem from a different video where we were multiplying polynomials together. Let's look at this example right here. And after we multiply the polynomials together, it asks us to combine like terms. So on this step right here, this second step, we were combining like terms and we got this answer. So let's review what combining like terms is all about. These two terms right here, the one with the 4 and the one with no number in front of it, okay, which means there's an invisible positive 1 right there. Those are like terms, so we combined them. Just a reminder about what combining like terms is all about is that you add the numbers that are in front of the xy squared, and you can only do that because they're like terms, which means that the xy squared is the same in both of them, okay? And so we added the 1 plus 4. That's where the positive 5 came from right here. But then notice again, just reviewing here, that xy squared stayed the same. So when you're combining like terms, you add the front parts of them. Okay, sometimes you subtract if it's a subtraction situation, like right here, -4 minus 1 on this term. But you either add or subtract. But the key thing also is that the xy squared part, and also on this part, the x squared y, it stays the same. So it has to be the same. Again, looking at these two terms as an example here, xy squared and xy squared, that part has to be the same, the variable part, and then you add the things that are in front of those terms. It's the same thing when we're adding and subtracting radical terms here in this current video. Okay, if the things, check out this step right here. You don't need to look at the rest of the steps there. We'll see some examples anyway. Look at this step right here. Notice that we have three terms right here. And I need to back up for just a moment here. What does it mean to be a radical term? It doesn't just mean a radical necessarily. Sometimes it does. But a radical term is either just a radical only, or it could be a radical with a term in front of it that's being multiplied by it. For example, 8 is a term that's being multiplied by the radical 2. So the 8 radical 2 right here, that's a term. Not just the radical 2, but the whole thing I just boxed in right there, that's called a radical term. I just want to make sure you know what I mean when I say the phrase radical term. So that's a radical term. Okay, this is a radical term. And this is a radical term, okay? And they're being what? They're being added and subtracted, aren't they? Okay, thus the name of the video, adding and subtracting radical terms. Okay, when you're adding and subtracting radical terms, similar to combining like terms, if the radicals are the same, and the radicals need to be the same. And so, for example, this problem, you can't combine anything yet because they're being added together, but the radicals are not the same. Okay, if the radicals were being multiplied together, that'd be different. But with addition and subtraction, just like with combining like terms, if you're adding and subtracting terms, the variable part has to be the same. In the same manner, when you're adding and subtracting radical terms, the radical needs to be the same. Okay, and so we can't combine those together because they're being added and the radicals are not the same. Now that doesn't mean that we can't do the problem. I'll talk about that in a minute. We can make these the same potentially. Again, we'll talk about that in a minute. But for now, why was I able to combine these into this answer right here? Okay, it's because the radicals are the same, and so you can add the numbers that are in front of each radical, okay, add or subtract them, 8 plus 6 minus 4, okay, and that is equal to 10. 8 plus 6 is 14 minus 4 is 10. And notice, just like with combining like terms, you guys, the radical 2 was the same in all of these terms, and it stayed the same, okay, in the final answer, just like it did with combining like terms. And so what we do is, in these problems that we're going to do in this video, is that if the radicals are not the same and they ask us to add or subtract the radical terms, and you can see here we have two radical terms that are being added. Okay, there's an invisible 1, by the way, in front of this radical. So this is a radical term, okay, a radical times a term in front of it. It's just invisible. So we have two terms being added together. The radicals are not the same, but we can attempt to make them the same. Okay, and if we're successful in making them the same, then we can add the radical terms together just like these up here. So let's try to make them the same. How do we do that? The way we do that is we simplify the radicals in the hopes that, because just a review here of simplifying radical terms, when you simplify radical terms, the goal is to make the number underneath the radical smaller. This went from 27 to 3. We're going to do that here. We're going to simplify in the hopes as we simplify these and make the number smaller underneath the radical, we're going to hope that the number underneath the radical ends up being the same for both of these radicals here. Okay, so let's see if that happens. And just a review here, how did we simplify radical terms? And we'll do that with, let me just write it down here at the bottom of the problem here as we review the simplifying process. Okay, we're going to try to simplify these two radicals separately. I wrote them down here at the bottom because it's separate from the problem itself, as you'll see here in a second. So I'm just going to put it separately down here, and then we'll go back to the regular problem here in just a moment. Radical 12. Remember, since that's a square root, our first goal is to factor out, just like we did here with the 9, factor out something that is a perfect square. Remember the perfect square numbers here. The largest thing on the perfect square list that can be factored out of 12. Wouldn't that be 4? Okay, because 9 wouldn't factor out of 12 and everything else is too big. So I can do 4 and 3. I'm going to, something I didn't do in the previous video, which we're ready to do now, is notice that in these problems that were done in a previous video, I got them right here, you didn't really need to write down this first step right here because it was just going to be the same thing as this except for it's separated. So you can actually jump from the original problem down to this step. I'm okay with you doing that now. I just wanted you to see, as we look at this here, I wanted you to see how that property works, where it breaks down. But now that you can see here as we review it, and you can see that that works on all of these. Okay, if it's a cube root, you've got to have 2 cube roots. But if they're being multiplied, you can split it apart. So you really don't need to write down this step right here. You know it's already going to end up being this, okay, where it's split apart. The numbers are the same, so you can jump right to it. So instead of writing 4 and 3 inside of a single radical, you can split it apart now, just like we did with the 9 and the 3 in separate radicals. And then remember that what we have to do after we simplify the radical, after we split it apart, is that we then take that radical that had the perfect square number in this case it's 4, and we actually figure out what that radical is equal to. The square root of 4, as you know, is equal to 2, and so that is square root of 12 simplified right there. Let's do that same thing with square root of 75. What is the largest number on the perfect square list that will factor out of 75? It's actually 25. You can double check that if you don't see that. That's good practice anyway to just go through that process. But it's 25, and 25 times 3 is 75, and so it splits apart like this. Okay, and 25 is the biggest number on the list that will factor out. Square it, and remember again, after we pull out the 25, we then, since 25 came from the list, that's the one where we figure out the radical. Square root of 25 is 5, and so we end up with 5 square root of 3. Okay, so here's what you do. We simplified the radicals, but we're just getting started here, okay? What we now need to do is just a few more steps here. What you do is you bring those simplified answers back up here, and you replace the square root of 12 with the 2 square root of 3. You still keep everything else there. You got to keep the 5 there. Okay, you got to keep the plus there. Let's bring that down. But you replace the square root of 12 with 2 square root of 3, and you replace the square root of 75 with 5 square root of 3. Now, if there was something in front of the original radical, like the 5, for example, that's still being multiplied by the thing that you replace the square root of 12 by, which is the 2 square root of 3. So that's why I put the multiplication symbol right here. okay, there was an invisible 1 right here. You don't need to write that. If you had written 1 times 5 right here, it wouldn't have changed anything. It still would have been 5, as you'll see here in a second, because the next step that we're supposed to do after we do that is we're supposed to multiply the part that's already on the outside by the 2. Don't multiply by the 3. Okay, what we have here is we have a regular term multiplied by a radical term. The way you multiply, you guys, a regular term times a radical term is you never multiply something on the outside of the radical times something on the inside. What you got to do is you got to multiply outside times outside. Okay, and then you just leave the radical the same because there's just one radical there in this multiplication right here. The plus sign separates this part. Don't touch that part yet. So we have 5 times 2 is 10. Again, don't multiply anything by the 3. And so we have 10 square root of 3. Bring down the plus. Now, there's that invisible 1 right there, but if you did 1 times 5, again, it's still going to be square root of 5. So if there had been no number in front of the original radical, like you can see here, you really don't need to do this step here where you got to multiply the outside parts like we did with the 5 and the 2. You can just bring the 5 square root of 3 down. And now what we got, you guys, is the same thing we had up here in this example. You have 2 radical terms. This one and this one. You don't have to box it in. I'm just highlighting it here. We have 2 radical terms. They have the same radical now. And so you're allowed to add together, since this is an addition problem, those numbers that are in front of each radical, just like I did with the 8 and the 6, and then I eventually subtracted the 4. Okay, so 10 plus 5 is 15, but remember, don't just say 15. Remember that just like up here where the square root of 2 was all the same here and then it stayed the same, when you're adding and subtracting, again, this is just adding and subtracting. It's not multiplying radical terms or anything like that. It's just adding and subtracting radical terms. When you're adding and subtracting radical terms, the radicals need to be the same as they are, square root of 3 and square root of 3, but then the square root of 3 stays the same. Okay? And so there's your final answer right there. Let's try that again over here. The only difference is that now you have cube roots. Okay, we'll review how to deal with cube roots again here. Okay, we need to simplify first, just like we did in the problem that we just did. Okay. Now I want you to notice something here. This radical right here, this is rare, but it does happen sometimes. This radical right here cannot be simplified any further than it already has. Let me show you why. Okay. With cube roots, you have to look at perfect cubes, okay, on the perfect cube list. If you're and notice there's no number in front of the variable, so we don't do this part of the list right here. But when you do the variable part, you have to pick out one of these exponents. Just to review with you here now, remember that in order to pick an exponent on this list, you've got to pick the largest exponent that is not bigger than the exponents you already have. Well, guess what? All of these exponents are bigger than the exponents we already have, x to the first and y to the second. So the third power is too big for both of these. And so therefore, I can't factor anything out of either x to the first or y to the second. And so therefore, this is already simplified because you can't, there's no number in front that you can do anything with, like if you had 75 or 12. Okay, and then the variable part, the exponents are too small for even the smallest exponent that we have available to us in perfect cubes, which is the x to the third. Now, on this part, we can simplify part of it. Okay, so we need to do that. If you can simplify any part of it, you need to do it. So, again, reviewing how to simplify. If you have more than one variable, you do one variable at a time. If there's no number in front of the x to the fourth, then you don't need to do that part. You don't need to do the 1, 8, and 27, all that stuff. But we do the variable part. What's the largest exponent on the list that is not bigger than x to the fourth? That would be x to the third, right? So we factor that out. Now remember, if I do y to the second now, if we again ask the question, what's the largest exponent on the list that's not bigger than y to the second, all right, there is no exponent on the list that is not bigger than y to the second. They're all bigger than y to the second. Okay, so if you get an exponent that's bigger, or pardon me, smaller, like we did over here in this radical, if you get an exponent that is smaller than all the exponents that you have available to you, then you can't factor anything out. So we can't factor anything out of y squared, so we just do the x to the fourth, and then we split it apart like we did over here. Okay, all in one step here to make it a little bit faster. Oh, I didn't write down enough there. What is x to the third, you guys, times what is equal to x for y squared? Well, you know that you have to have x to the first right here because 3 plus 1 with the exponents equals x to the fourth. And then what happens is if you have a variable and you didn't factor anything out of that variable, you bring the whole thing over to the second part. Okay, the whole thing. Okay, and you'll notice now that x to the third times xy squared, if you multiply those together, it does equal to this. So it does work. Okay. And then just like we've been doing when we simplify, we then figure out what that first radical is equal to that has the perfect cube stuff in it. Okay. The cube root of x to the third is just going to be x to the first. Okay. Because x to the first, if you take it to the third power, it's equal to x to the third. And so going backwards, the cube root of x to the third is x. Okay, so what we do, just like we did here, is we go back and we plug in what we got into the old radicals. Now this radical, we're not going to do anything with it because it's already simplified. There's nothing new to plug into it. So we're going to leave that one alone, okay? Since we couldn't do anything with it. However, the other one, we have to plug in the simplified answer to that. Okay, so we got x cube root of xy squared. Okay, that got plugged in. That replaced this right here. Okay, the 4 is still there, just like over here. The 5 was still here. And then the plus 5x is still there as well. Everything that's on the outside of the radicals are still there. And then remember, this radical didn't change at all, so I'll just write down the same thing we had originally. And then just like we did here in this problem over here, what we do is that if there was something already on the outside of the radical, we multiply that by the new thing that's outside of the radical after we simplified it. Okay, and just like when we did 5 times 2, but don't multiply by the inside of the radical, same thing here. We do 4 times x, but don't multiply by the inside of the radical. So we just have 4 times x, which is 4x. Radical just stays the same. And then here, because this didn't simplify at all, it stayed the same. There's not 2 different parts to multiply here, like we had with 4 times x and 5 times 2. This just stayed the same, so you don't need to do that thing where you multiply the outside parts here. Okay, because it stayed the same. There wasn't 2 different parts to multiply like with the 4 and the x. Okay, so what we have here once again is we have 2 radicals. You got to do that step where you multiply the outside parts so that you know what you have on the front of each radical here. We now have 4x and 5x. The radicals are the same. That's the key part. Since we're adding the radicals, the radicals need to be the same. Otherwise, you can't combine these into one term. Combine these 2 radical terms into one term. But because the radicals are exactly the same, we can add the 4x and the 5x just like we added the 10 and the 5. 4x plus 5x is 9x. And then, just like in the last problem, just like in the sample problem up at the top of the page, the radical is the same and it stays the same. And you combine it into a single radical term. Okay. We have 2 more problems here, very similar. Okay. I'd like you to go ahead and give it a try here. I'd like you to encourage you to do that. If you could just turn off your video here, or pause your video, excuse me, for just a few moments. Try those 2 problems, and then we'll look at the answers for those, including the work, after you turn the video back on. Okay, let's take a look at number 1 right here. Remember, we need, since the radicals are not the same, we need to try to make them the same by looking at the radical the radical equivalents here, okay? And so 45x, in other words, we want to simplify the radicals. 45x and 20x, we bring those down here, okay? And we simplify them. What happened was I do the 45 first and then the x. Okay, you got to do those separately when you simplify radicals. 45, you're able to factor out a 9. And then the x is x to the first. And since x to the first is smaller than any exponent you have on the perfect square list, okay, you can't factor anything out of that. So you just leave the x alone, okay? And so you just factor out the 9. 9 times 5x is 45x, so it still matches up, but you were able to factor out the 9. You then split it apart. You don't need to write down this step right here. I got a little bit heavily detailed there, but you don't need to write that down. So you could just jump to this step. That's fine. And then we simplify that first part there again, or we figure out what it's equal to. Square root of 9 is 3. And then that is your your simplified radical term. Same thing happens with 20, where you factor out a 4. 4 is the biggest thing on the list that you can factor out of 20. Okay, again, you can't factor anything out of x to the first because x to the second is too big, as is all the other exponents. Okay, and we end up getting 2 square root of 5x. Just like we did in the first two problems, after you simplify these, you then go back and you go back and you plug them in. Okay. And we get 3 square root of 5x replaces the 45x, and then 2 square root of 5x replaces the square root of 20x. We then multiply the outside parts, just like we learned in the first two problems. We get 15 and 4. And then since the radicals are the same, we are allowed to do 15 minus 4, which of course is 11. And we were able to combine it into a single term because we were subtracting two terms that had the same radical. Okay. Number 2. Okay. We have these two radicals here. They're not the same, so we need to what, you guys? We need to try to make them the same here. Okay, so I did that here, and fortunately they did end up being the same. Okay. Remember, for 24, x and y to the third, you got to look at all of those separately there. 24, I'm able to factor out 8. Remember, we're looking at the perfect cube list. Okay, 8's the largest thing you can factor out. Okay, out of 24 from this list. You can't factor anything out of x to the first because x to the third is too big. But you are able to factor out y to the third. Remember, you're allowed to factor out an exponent that is on the list. It doesn't need to be smaller. Okay. Or pardon me, it doesn't need to be bigger. The thing on the list, in other words, doesn't need to be smaller. Okay, if it's the same exponent as something on the list, factor that out. Okay, because that'll end up being the biggest thing on the list that is not bigger than y to the third. Okay, so if it's the same, you're allowed to, and you should factor that out. So y to the third, we factor that out right here. Okay. What we have left, in order to still make it equal to 24x y to the third, we have to multiply by 3x. Okay, we split that apart, which you can, again, do that right away. You then figure out what that first radical is equal to. And if you were to take 2y and cube that whole thing, it would be equal to 8y to the third. That's why that radical is equal to 2y. Very similar thing over here. Actually, no, it's a little bit different. Excuse me. 81, 27 is the biggest thing on the list. You can factor out of that. Okay. X, because it's x to the first, and because x to the third and all the other exponents are too big, you can't factor anything out of that. And so we have 27 times 3x, split that apart. Okay, and then the cube root of 27 is 3. So we've simplified the two radicals that we have here. Okay, and then after we simplify those two radicals, we go back and plug them in. Okay. We replace this radical with the simplified equivalent. We replace this one, but remember the plus y is still there. Bring that down. Don't forget about it. We replace the radical with this, okay? And then remember this, we're on that step now where we need to multiply the outside part. Since this didn't have an outside part, okay, kind of similar to the 75 problem over here, okay, since there's nothing outside the 75 in front of it, you don't need to do the multiplication step here. The 5 squared to 3 stays the same. It's the same thing here. The 2y stays the same. There's not two different things being multiplied there, but here we have two different things, y times 3 on the outside, so y times 3 is 3y. Once again, the radicals are the same, so we are allowed to add the 2y and the 3y, and we get 5y with the radicals staying the same. So that's how you add and subtract radical terms. Okay, make the radicals the same, multiply the new outside part, if you were able to simplify it, by the old outside part. Okay, and then if the radicals are the same, you're allowed to add or subtract, if it's a subtraction problem, the things that are in the front of each radical being multiplied by the radicals, okay, as you're keeping the radical the same. Okay, so that concludes adding and subtracting radical terms.